This course, Gas Turbines, Design and Analysis, it's a very complex course which draws heavily on thermodynamics, on second law of thermodynamics, on heat transfer, on fluid mechanics, on compressible flow fluid mechanics, shocks, supersonic, subsonic flows, all of that stuff. And you would think that it may just apply to nozzles, but no, all throughout the compressor blading passages, you have to worry about these things. So any one component of this course, we're going to be doing cycles for about 5 weeks so that we can all feel good about thermodynamics and cycles. Yeah, I got this. And then we're going to get into components, which requires a whole lot of depth. But I'm going to try and make the depth all one-dimensional. We're going to try and do this so you get a basic idea of how these things work. The cycles on how they work as a system, and then the components, how they kind of work mechanically. So that's the idea. So the course outline, I do want to talk a little bit about the history of gas turbines. It's kind of an interesting subject. And then we're going to get into the various types of engines, single shaft, split shafts, a whole bunch of variations on land-based or marine-based engines. We're going to get into aircraft components, turbojets, which no one uses anymore, turbofans, turboprops, and there are variations. Not all of them, but just a few. Then probably around the 5-week mark, we'll probably be getting through a little bit of combustion. And if you've had the IC engines course with Professor Cohort, you probably know all the chemistry already. But if you haven't, we'll go over it again. There's a lot of ways to analyze gas turbines. You'll hear the term cold air standard, which is a fancy phrase for constant specific heats taken at room temperature. There's a hot air standard, which is variable specific heats based on the temperature that actually exists. There is the air equivalent, and we'll talk about that a little bit later. There is the actual medium, which is a bare, because it requires a combustion analysis and treating the gases after the combustor as gases and not air. So carbon dioxide, water vapor, and whatever else is going out. And that is a little tricky. But we're going to get into the mechanics of flight, inlets and diffusers, particularly with ramjets and supersonic aircraft, turbo machinery. We're going to spend a lot of time on compressors. There's a lot to deal with. It's a compressor. In Thermo 101, the compressor was like a circle, and it had an inlet state, and it had an exit state, and the power of the compressor was m dot times h2 minus h1. That's not exactly how they work. There is a device, a physical device, a shaft that is turning the compressor, putting power into the compressor, and then there's a whole slew of stuff that goes on inside the machine to pressurize the air, to get it to move. So we're going to be talking about that. And there's a little bit of a sailing component because the compressor rotors are airfoils. So we're going to have pressure loads and how much of the compressor spinning is impulse, how much of it is reaction, meaning a delta P across the blade, like Bernoulli's equation. That's how an airplane flies, through a reaction force. So it's not the circle with the thing on it. For the first 5 weeks, it will be. And then that'll all change with vector diagrams and all of that. Turbines, I'm not going to spend a lot of time on turbines because basically the compressor is the more finicky engine. It's a lot easier to let a gas expand because it wants to than to keep it bottled up. So compressors are definitely the pain, and turbines are not so bad. Afterburners are nothing more than combustors, and then we have heat exchangers. We have some interesting new topics that are, one's called component matching, which is, okay, usually as a student, when we design something, it is a design based on a full load. I got 100% load, and this is what it's got to do. But these beasts, these gas turbines, they don't hardly ever run at 100% load. In the power industry, yes, because they're making smaller units that they can bring online, but they want them to run at 100% load now so that they can run peak efficiency. But prior to now, in the real world, they ran on partial loads, And when they ran on partial loads, their efficiencies all changed. And it was, you had to match the right compressor with the right turbine and have it fit on the right performance curve. And where does it fit on the performance curve? So we'll talk a little bit about performance curves a little bit later. So component matching, off-design performance, and hopefully, if we have time, I would like to get a little bit into pollution. From the chemistry side, that's a nightmare. It requires an equation called the Van Hoff equation and other equations which are not user-friendly, equilibrium constants, whether or not you are going to get a species which is carbon monoxide or a species which is some other form of carbon, and it all depends on pressures and temperatures. So we'll talk a little bit about that, but again, it's a one-dimensional analysis, so it's not going to really talk about the stratification inside a combustion chamber or anything like that in some design projects. So that is the gist of the course.